Right. So let's just get started. It's not just us versus them. It is just we. This is our responsibility. So whatever I'm about to show y'all, please be responsible with what y'all do with it. So who am I? I'm Jayden Furtado. I've done my bachelor's in computer engineering from the University of Mumbai. I'm an engineer at Rudra Cybersecurity. We are a small startup in Mumbai. I secure open source software, websites, governments. I'm helping build the world, protect websites, protect industrial control systems, software-defined radios, AI models, and much more. And yeah, Windows. I know this is the reason I usually would do my presentations in Linux. Unfortunately, Linux is not cooperating with me today. And I'm also a part-time keyboardist and a musician. Yeah. So again, this is our responsibility. This research was done in good faith because we care. This is built off previous work which I've done over the years when I was a student. I am not an OT expert. Okay, purely done. Most of my work is related to web security. All findings have been disclosed to the authorities for educational purposes only. Again, exercise sound judgment. I don't want any of you all winding up in jail. And again, disclose your research to the authorities. Common sense, just because you can doesn't mean you should. And yeah, so when I was preparing the presentation for today, my slides crossed 120. And then I realized, because there were so many findings, and I initially was going to go layer by layer from the Purdue model, going all the way from the IT infra, coming to the physical processes themselves. And I realized that it's not going to be contained within 40 minutes. It's going to take a lot more time than that. So maybe in a month or two, I'll be releasing a white paper where I'll be detailing all my findings in full technical depth. And if anyone's interested, they can take a look at that. So in the interest of time, we'll just get straight to the problem which we found, and that's this. So we asked 3 questions, okay? Is it possible for a low-skilled attacker to gain remote access via the public internet to sensitive systems of the railways? How difficult is it to pull it off? Can we prove that a novice could do it? And finally, if yes, what's the worst thing that an attacker could do? And the answer to all 3 of them, including the last one, is yes. Okay. And this is the vulnerability we found. So just to simplify, if it's not very clear, this.username.equals ignore case admin and password underscore view, this.password matches the password. That was the vulnerability we found. And I assure you, this looks trivial, but this is enough to shut down the railways of entire continents. Just to give perspective. And other concerning findings was passwords being sent via get parameters in URL. And of course, they got archived on webarchive.org. And passwords being entered on YouTube videos, which then someone uploaded to YouTube. Okay. And these are actual systems. Okay. And we had many more concerning findings. But these were the ones which took the cake. And so the answer to question 1 is yes. Literally anybody could find critical stuff. It's literally available on YouTube. It's available on Google. You just need to know what to search for. So context 2, 2 years ago at Nullcon Goa, 2022, I was attendee for this particular talk. Raining CVs on WordPress plugins. It was by Shreya and Shiraz. And their research was something which appealed to me, wherein they basically use SemGrep, semantic grepping, where they did a semantic analysis of code of WordPress plugins, and they found a bunch of 0 days in said plugins. I adapted that for my final year thesis in engineering. I took the topic of scanning open source software for 0 days, wherein we scanned basically around 10,000 repositories of GitHub, and we tried to find 0 days in them. One of them we found, and we presented it at Nullcon Goa in 2023. We presented a tool called Scanary. That's the link to it. It was a wrapper built around SemGrep, ORT, which is open source repository toolkit, a review toolkit, and GPT-3. and it basically did semantic grepping of your code, found vulnerabilities in it, and GPT-3 was there to suggest fixes for the findings. So on a side quest, because the project was supposed to take about a year, we completed it within like 2 or 3 months. We decided to mass scan Google Play Store. And during that, we did it on a budget. So my dad, he works at his office, and they were about to throw out one of the old PCs. So I told him, like, okay, don't throw it out, give it to me. I repurposed it for scanning Google Play Store apps. And we basically followed a very similar pipeline to what I had done previously, which is over here. We just had to adapt semgrep to be able to handle the APK. So we had to decompile it into Java. And we were able to basically mass scan Google Play Store apps. And we found stuff like this, wherein we had Redis databases and passwords hard-coded into the application. We found a number of AWS keys with a lot of bad stuff which could be done with it. And in the end, this is our result. So we scanned 1,000 apps. 23 of them had critical vulnerabilities. A bunch of APIs, keys, and passwords, exposed Firebase DBs. Many outdated libraries with known vulnerabilities were being used. Apps had insecure permissions. People were using HTTP instead of HTTPS. And again, all findings were disclosed. But we missed the bigger picture. In all of this, whatever we found, there were a lot of critical things. But the one thing I didn't ever think of is to make a connection between Google Play Store and critical infrastructure. And so before we continue, let's go back in time. So about 100 years ago, we had trains which looked a lot like this. They ran on steam and they ran on coal. The driver in the train would have seen stuff like this, where you had valves and you had levers, and adjusting the valves and levers would perform various actions on the train. The control rooms would look something like this, where you had levers which would be used for switching tracks. Forward 100 years, and we have trains that look a lot like this. Okay, this is a train I've just taken one from Google. You have drivers who, when they sit at the controls, they have controls which look very similar to this. And you have control rooms which look a lot like this. Now, one major difference is that there's a lot more computers today than there were previously. And when there are computers, people usually make mistakes. Now, most of the times, and a good argument can be made that computers reduce human error. You can replicate actions again and again. Computers don't get tired. The problem is there still are humans in the loop. Humans are in the loop at the start when they are programming the computers. There's humans who are in the loop when they are installing the computers. And humans are in the loop for operating the computers. Now, in all three cases, and in all these 3 points, there's a lot of room for error which can occur. So let's start by analyzing the system. Now, given my background as a computer engineer and as an engineering student, we took a class in system design. And so let's say we had to design a system from scratch, given these requirements. So the control room needs to know the position of all trains so that they can control traffic. Drivers need to know their position with respect to their where they want to go versus where they are right now. Signals and track switching should take place in a way that it is safe at all times. So let's just say tomorrow, for some reason, the power gets cut and all trains come to a halt. Or if, let's just say, power gets cut to the servos which are operating the trackside controls, but the trains themselves are still operational. They should operate in a way that even at the time of failure, everything is safe. Control rooms should be able to manually override certain PLCs and certain signals. Just in case there's a failure, you want to be able to override stuff. So that you've got like a break glass mechanism. And finally, drivers and control rooms need to be able to communicate with each other. So if we had to design a system, this is something we would come pretty close to. This is a standard in Europe, the European train control systems. We've got a bunch of different devices on board, all of which communicate via GSMR to the control rooms. The control rooms can switch tracks. There's something called as the interlocking mechanism. And we don't really need to go in depth on each component, but this is a high-level view of the stuff which is in place right now. And from a business perspective, as we move further, what is becoming more increasingly common is that you've got third parties who build hardware, you've got third parties who build software, you've got system integrators who will combine the hardware and the software, and finally you get your end product, which is the train. Now, again, this is from a security perspective, from a business perspective, it's really good. It means that you can offload a number of the amount of cost, the components become a lot cheaper. The problem is, from a security perspective, there's a number of faults which can be introduced at different places. Maybe the hardware manufacturer can have a mess up, and there's a vulnerability which gets introduced over there. Maybe the software manufacturer makes a mess, and you've now got a vulnerability in your software. Or maybe the system integrator themselves don't actually configure the end hardware and software correctly. Maybe they leave it in debug mode, and you've got a problem over there. So, we come now to the EVC. So, if I continue, EVC, which is the European Vitals computer, this is at the heart of modern trains. Okay, you've got the EVC, which sits at the center. Any inflow and outflow of data, to the best of my knowledge, goes through the EVC. And yeah, it's basically at the heart of the train. It is the heart of the train. Any other component has to interact with the EVC. And the EVC itself is pretty complex. It's a beautiful piece of hardware and software. But at the end of the day, it's a computer. And so we take a little more look into the diagnostic systems. So this is something I didn't know at the time. But it turns out that the manufacturers and the operators want to know the current status of their trains and the status of software and hardware which is being used. And they've got a system which is similar to this. So most trains use a protocol called MVB, Multifunction Vehicular Bus. It's very similar to Modbus. You can query different key values. And it basically will send it via GSMR or LoRa to the edge gateway. Edge gateway then forwards it to the cloud servers, and where it's accessible to the manufacturers. Now, behind the scenes look of how all of this works is something very similar to this. One thing to note is that because I'm right now in Berlin, I have gone with the European standard. It should be noted that all major railways of the world have very similar systems. So, findings in one place usually affect findings in other places. And it also, another thing to note is that manufacturers who manufacture components for one country also manufacture components for the other countries. So if you find a vulnerability in one component, it's probably going to affect a number of countries together. So this is more or less the way the remote diagnostic systems work from a block diagram perspective. And it's very interesting, okay? Like when I first found out about it, I was like really interested. So what all functionality is exposed? Like, can we reach it from the internet? Like, could we find a vulnerable piece of code? And where does one find such software publicly was the question we asked. So after doing a bunch of Googling, turns out you can actually find it on Google Play Store. Okay. And that leads us to this vulnerability over here. The admin username and password was hard-coded into the application. Now, at face value, it should be noted that this, when we read the documentation of the manufacturer, they say that, okay, it's read-only. You'll only be able to get metrics of the different sensors from the train, its location, diagnostic information, etc. It should be separated from the rest of the software and the rest of the system, so it's not safety critical. And we were like, okay, that's cool. But is it really isolated? And the answer is it's not. Okay, so this is ideally the way it should work. The component which is in red is the place where we found the vulnerability. Now, if you can actually notice, it interacts with the central server. Actually, okay, so if I had to just go with the flow of data, the diagnostic information is generated on the train. It gets forwarded wirelessly, which is then forwarded to the servers. The servers then act as basically like a high-level filter. It will filter out different pieces of information. So the control room doesn't necessarily need to know diagnostic information, so it won't forward that information to them. It will just forward the current location, the status of the train, and basically the place where the train is, and information with the driver. So if the driver has any queries which they want to communicate, they can communicate through the system. The remote diagnostic system is supposed to be strictly for diagnostics. You're not supposed to be able to do anything else with it. You're only able to see if there's a fault. If there's a fault, you send out the engineers to the train and they can do whatever they need to do. But we found an undocumented functionality which allowed remote software updates, so over-the-air updates to the EVC. And the EVC, again, like if going back to the previous slides, it's at the heart of the train. Now, let's just put all of this together. Okay, this particular piece of software was on Google Play Store. The username and password was hard-coded into it. And one of the undocumented functionalities was that you can push remote code to the EVC, which is at the heart of the train. It's pretty straightforward as to why it's bad. So software updates. Now, funnily enough, over-the-wire software updates is allowed. When you read the European spec, and this is one of the things they say, is that edge devices should facilitate the possibility to update their firmware and software so as to to roll out new functionality and patch security vulnerabilities. Unpatched systems are left vulnerable to attacks, and the last line is the most important. Okay, it should only allow this functionality if it is considered to be not safety critical. EVC is definitely safety critical. Okay, and this is the reality. So you can select locomotive number, you can enter the password, select file, configure program. Now, I've obviously changed the styling, but yeah, this is basically what we saw. And what was happening in reality is this. You've got the central servers, you've got remote monitoring and configuration management, but you can push configuration changes directly to the trains. And if you can start doing that, the least worst thing you can do at this point is break a train. Okay, you can pull off some really, really nasty stuff where you can suddenly cause it to conditionally fail. Maybe the brakes don't work all of a sudden. Maybe when you're trying to slow down the train, it starts accelerating. Maybe you try to lower the pantogram, but the pantogram just raises itself. All sorts of bad things happen. So the manufacturers were using the remote monitoring system for sending out updates. Modern devices and sensors on trains use Linux. And there's huge possibility for supply chain attacks because developers, from whatever I've seen so far, they just use pip install, whatever, -r requirements.txt, or maybe, npm install packages. And especially when you're working with critical infrastructure, it's a very, very bad idea. But let's be honest, if you've got vulnerabilities where you've hard-coded a password into your application, you probably have a lot more bigger problems to deal with. So, can this be done by a novice? Well, possibly. Okay, there's a lot of body of knowledge which went into the work which we did, but it's definitely doable if you are able to piece all the pieces together, which we had to. It should be noted that all of these we had to find from different locations. It's not just one particular document which you can refer to where you'll get all information. And so, say at some time T, a malicious attacker K, conducts an attack and performs a set of S steps to successfully control the EVC. What is the worst thing that could happen? Okay, so this is the thought process we had to do. It should be noted at this point, and I have to make this disclaimer, we did not push code to the trains because then I would not be speaking over here. I would probably be in jail. And that's the reason I started out with a disclaimer that there are probably other such apps. Please think about whatever you're doing. So you could possibly cause collisions. And this is I'm being absolutely serious. It's totally within the realms of possibility. Again, there's a number of different things which have to fall into place before you can cause a collision. I am not going to go into those things. But effectively, an attacker can poison the data. You can send false signals about where the train is versus where it actually is. And you've already basically just got access over all data which is coming from the train. So you can spoof locations, and that should be enough to trick the control rooms into maybe ordering a train to move forward when they should not move forward, or maybe ordering a train to stop when they should not stop. Right? Again, all of this is taken from public pieces of information. None of this is proprietary. We've not made anything up. All of this is available in the open domain. So in effect, the attacker at this point could basically control the remote monitoring system. All you have to do is find a vulnerability in the central servers, which are used for filtering out information, and you're in control of the trains at this point. There's nothing else which is left to do. You can make an argument that there's something called formal verification, where you ensure, like I said, graceful failure at all times. But formal verification is only good when the data which it is using is actually true. Here, in this case, we've just poisoned the entire data, so there's nothing to verify per se. Every particular piece of check and balance in place at this point is in favor of the attacker. The attacker is in control. So why is this a big deal? So attacker controls the EVC, they control the central data servers, and they control the control room servers. They can send false data to the control rooms. They can send false data to the trains. Formal verification fails because data can't be trusted anymore. And at this point, you've just got a botnet of trains. So you already control the EVC. The EVC is what sends information to the driver machine interface, the DMI. And it also controls input from the DMI to do whatever action it needs to do. All data is, you've anyway controlled the GSM at this point, which is the end servers. In effect, you've controlled the EVC, you've controlled this, there'll be n number of trains. You can just send out any command and they're probably going to follow it. Now, I hope there are certain manual or analog, I would say, changes which can be made, or analog switches which don't rely particularly on the EVC, so that there is some form of manual override which can be done. But this is basically it. So to sum it up, there were over 2,000 locomotives which were affected. Operators, the drivers, the system integrators, everybody were in the dark about this functionality. Poor engineering decisions were taken. There was lack of proper security testing of the software which was running. There were multiple glaring security issues, which the moment we looked at it, we were absolutely scared because these were live systems. Software used as a fix for fundamental issues, which it had no business being there, but it was still there. And on paper, the particular operator was really good, but reality, it didn't translate to reality, unfortunately. And can we simulate this? Yes. Unfortunately, Linux is not cooperating with me today. I'm on Windows. But effectively, Microsoft had come out with a game not so long ago called Microsoft Train Simulator from early 2000s. Does anybody remember playing it? Okay, sort of. Cool. So, right. So what most people don't know is that there's, I almost want to say a twin to that called OpenRails, which is fully open sourced. You can simulate a lot of real track movement, real train movement, and real systems. So what I've taken is a screen grab of the Deutsche Bahn, which is used by Germany. And those are more or less what the driver would see. So a lot of the heavy lifting has already been done. So if I had to create a solution, which I actually wanted to, and demo it for y'all, you would have the HMI. You will have OpenPLC. You can use whatever protocol you want for communicating between the two. In this case, for the diagram purpose, I've chosen Modbus. It could be anything. It could be CAN bus, train bus, multifunction vehicular bus. All of those work. You've got the physics engine, which simulates the physics for your PLCs and your trains. You've got a state database, which can be used for mapping the state of the train. So whether the train is started, it's stopped, the current temperature of your compressor, brake temperature, all of that. And finally, it just translates to visualization. Like I said, OpenRails, it's open source, fully open source. I highly recommend people y'all give it a try. You've got basically a lot of the heavy lifting has already been done for you. The only thing which is left is to write a wrapper around this, which allows communication in the respective protocols. And yeah, and then you're in business. You've got a digital twin for the railways. I've seen a lot of companies spending millions and billions of dollars for creating these digital twins. In reality, most of the hard work has already been done and it's in the open source domain. There's another package I don't think and this was some of the cool stuff we were doing, wherein we were simulating actual models of water treatment plants and all of that. And all of them behind the scenes are using the actual protocols and actual PLCs for getting the work done. So what about other manufacturers? This was one manufacturer. There are dozens and dozens of these. There was a particular manufacturer called Nevag from Poland, and they had basically put DRM inside their trains. It's a pretty good talk. It's on YouTube by this group of hackers. who found that this particular manufacturer was engaged in anti-competitive activities, wherein they basically just stalled the EVC and they stalled the trains using software. They basically put a check in place so that if the train goes within a certain geolocation, the train just bricks. And it was not documented. So that's something very interesting which we found. We didn't find, when we saw it, it was like, okay, that rings a bell. SCADA Strangelove, this is another talk which is on YouTube. I highly recommend watching this. Okay. They've gone into much more technical depth than I have regarding protocols, the vulnerabilities, different problems which are faced. And have you seen such a similar thing before? Like from all of this, whatever I've mentioned so far, it should ring bells regarding MCAS in Boeing. Okay? It is not an exact analogy in that over here there was no cyber threat per se, but there's a lot of things which we can make a comparison with. So MCAS was initially considered not safety critical. It was not documented in the manuals. In fact, Boeing actively went to try and remove it from the manuals. It initially just relied on the angle of attack sensors for making any judgment. Management pressured engineers to remove it and for coming up with engineering workarounds. And there were poor engineering decisions which were made in the end. And that cost people their lives. Okay. Now, software was being used as a fix. That's basically what happened. So what can we do about it? We know there's a problem now. We know that there are certain things which are not happening and should not be happening the way they should. So for engineers, please say yes to safety. I have to beg of you all to do this. Even if you're building a website or an app, and if it's just going on Play Store, you never know when it might come back to bite you. Okay. In this case, I'm sure the developers of that particular Android app had no clue that they were exposing critical infrastructure. To their mind, it was not safety critical. But testing of systems is so important, so important. Sound design and engineering solutions should be in place, please. And it doesn't really matter whether you're building a game or if you're building even a static website. Please ensure that security has a place. Please say no to hiding functionality and safety issues using software. It's not a good idea. Hacky solutions should not be in place. Please don't cut corners and add unintended complexity. For the system integrators, please ensure there's redundancy. So in this case, again, I'm 99.99% certain there's manual overrides to the EVC. So please ensure there's redundancy in your software. Understand everything which is going into your end component, because in this case, things could really have gone bad. It's us, we reported it to them, but it could be someone else who does not report it. Test the end systems exhaustively. This was really trivial to find. It didn't take rocket science to figure out. And for the executives, the first question which I always ask is, would you travel on your own trains? Okay. Please, it's a serious question. Would you genuinely travel on your own trains? When you know there's such safety critical problems which are there, that's something to keep in mind. Work with and not against your engineers. You all are all on the same team. Okay. Right? Everybody wants to succeed. So don't pressurize your engineers into cutting corners. Okay. That's again something so important. And good for business does not necessarily mean it is good engineering. The converse is also true. But especially in this case, because in business, you're generally trying to increase profits, but at what cost? And finally, for the regulators, so do you actually have complete oversight of the systems which are in place right now? So the particular app was pen tested, and the manufacturer also has an ISO 27001 certification. I am not entirely sure what happened over there, but it was, again, very interesting, because we found it using just grep, the password. And now, I'm not saying there was foul play over here. What I'm trying to say is that not misrepresentation, but incorrect interpretation. So when you're measuring data or certain statistics, are you interpreting them correctly? That's the first question which I always ask my people. Okay, you say there are only so many vulnerabilities which have been found. But what makes you say that there are only so many vulnerabilities? Like, what's the proof? Like, what's the measure which you're measuring, and how sure are you that it is effective? Regulators, engineers, executives, I actually suggest everyone over here. This is a white paper which was published by Deutsche Bahn and SNCF. It is available on their website. Please give this a read. Okay, the Internet of Railway Things Security. The findings in it are amazing. The mitigations they've suggested are also amazing, and they've actually addressed every single thing which we found in our research. So maybe it's time that engineers, like I hate to read white papers, but when they are like good white papers and they can add value to you, I suggest to like read them. And financial impact. So this I have taken from AAR, which is American Association for Railways. If the railways of America had to shut down for just one day, it would cost $2 billion. And that's just America. So if you had to shut down, let's just say Europe, you could basically just stall the economy as a whole and of the world. Because we are now living in a globalized society, changes which affect one country usually transcend to the entire world. We actually saw this firsthand when the Ever Given, the ship got stuck in the Suez Canal. Yeah, bad things happened to the entire economy. And the last thing which, before I conclude, is what's the true cost of getting things wrong? Usually, when they involve CII, it will be the cost of life. Now, you can make an argument telling me that, okay, these vulnerability, whatever has happened over here is due to human error or due to a failure of the machines. But my question to you would be, can you prove to me that these were not caused because of a cyber incident? The answer is going to be no. Because from whatever I have seen from the outside, and I don't know how true this is in reality, there aren't many checks and balances in place on the railways. Okay, people say it can't happen to me, but it could happen to you and probably will. So you need detection mechanisms in place for your trains. Okay, you need to ensure that such things don't happen in the future because they probably will. Right now, again, I have to keep saying this. We disclosed it responsibly. Another attacker might not do that. They could just sell it on the black market. They could sell it to a nation state. And it would not end well for you. And the main takeaway from this talk is the expectations versus reality of industrial control systems and their security. So people usually think you need like these, you have to be like this genius hacker, you need to have like zero-day exploits, you need to have like custom ISAF exploits which like maybe Stuxnet. But in reality, to succeed, the bar to entry is incredibly low. You could probably just do it with default passwords, like PLCs are maybe just not configured correctly. Maybe you've got an app on Android, on Google Play Store, which is exposing functionality which it should not. And so there's so many more questions which need to be answered, which I can't do on my own, but y'all are here, and y'all are really good hackers, and I hope y'all are also like really good human beings, which I'm sure y'all are. So I need your help. I need the help of regulators. I need the help of good hackers and good people. So a lot of things are published on Google Play Store every day. A lot of those things should not be on Google Play Store, especially if they are related to industrial control systems. So maybe something which could be done is to look at what else is related to ICS on Google Play Store. The next question would be how much of critical infrastructure is actually exposed because of Android apps? What's the impact? Which all domains of critical infrastructure do they affect? Does it just affect like what I found, transport? Or does it also affect energy and maybe medical devices, waste treatment, all of that? Can they be abused by a novice? What is the worst impact that can happen if they abuse? And finally, I hope I can like have a talk with someone from Google and maybe Apple, because I think they can also help with this. Maybe they can have like a check in place where if an app does not meet a certain security score, they don't publish it. So that would go a good way in like ensuring the security of the entire ecosystem at large. Maybe that's something we can talk about. I know Google already has this thing called Secure. I'm not entirely sure if I can get the name right, but they scan the app for malware. Maybe something could be done to check if the app is actually secure or it's not. And so why should you care? Well, you should care because we have to try and make the world a better place. So there's a lot of people who would want like bad things to happen. I think as hackers, as security engineers, as professionals, it's our duty to make the world a better place. We can do that. Okay, we should not shy away from it. And yeah, whatever findings, please disclose them. And so, in conclusion, to everyone, safety and sound engineering first. Okay, money, it's good, but not at the cost of lives. So, thank you. That's it from me. Yeah, any questions? Yeah.
Hello. My name is Andreas Bog. I'm responsible for information security at a train manufacturer. I'm glad it's my first day hearing from you because that's not my trains that you just showed.
Yeah.
There's something very comforting I want to tell and something that's rather scary. The very comforting thing is that the railway industry has 125 years experience in safety. Mm-hmm. They don't trust computers. There's a system, there's a button that the driver sets in. If you press that button, that punches a hole into a hose, and the pressurized pipe loses air pressure, and then big springs toggle the emergency brakes. So it's possible for the driver to stop the train without moving electrons. So that's the good news. Now comes the scary part. There's 3 words for you: automatic train operation. Yeah. So I would say, as an industry, we begin to understand the scope of the problem, right? And it's a big industry. It takes years to change. But, people have woken up. Regulators have woken up. The safety and railway government institutions know about the problem. Standards are being introduced. Our customers are coming to us and they start saying, we want secure trains. Do they understand what a secure train is? I would say about half of them does and the other don't. So we are in a good base. So thank you for the research. This helps pushing us forward.
Thank you.
Hi. Can you talk a little bit about the responsible disclosure process that you went through? How was their feedback and so on and so forth?
That's a good question. So we didn't go directly to the manufacturer themselves. We just approached the government and of that particular country, and they took it onward from there. So usually we avoid going directly to the manufacturer unless they've got how do I put it? If they've got a responsible disclosure policy themselves, then we'll happily, we are more than happy to work with them directly. But in more cases than not, we find it safer to approach a government body, and we'll send out an email to them. We've got contacts in different governments. We'll straight up contact them directly. Welcome. Anyone else? All right, cool. Yeah, if anyone wants to talk to me in person, I'm going to be here.